Good morning, everyone. In this session, we are going to start a topic called circular motion and a rotatory motion. About these two things, you will be learning in the later chapters in detail. All right. But for time being, in this chapter, the name of the chapter we are continuing is Motion in a Plane. In this chapter, whatever is required for us to understand the further concepts and the further chapters, this is the topic is placed here: circular motion and rotatory motion. All right. So the basics only we are discussing in this chapter. In the next chapter called Laws of Motion, you will learn a lot of things related to circular motion. And in the next chapter called Rotatory Motion, you will learn about this count. All right. Let us start the concept called circular motion and rotatory motion. And we have just finished our projectile motion. Once you come to the actual offline classes, there are so many things involved in projectile motion. Those things also will be discussing. So that means they are a little advanced level of the topics. Now, see the circular motion again. Imagine a particle is moving in a circular path. Okay, see, let's have a look here. This is a particle. Imagine it may be a car, a man, whatever. A particle is moving in a circular path. The circle may be small or the circle may be big, right? So circle may be small or circle may be a big. Look here. A particle moving in this circular path, moving in this circular path, whatever it is. There is no fixed axis. For this circle, this is the center. There is a straight line distance between the center and the position of the particle that's called radius of the circle, SR. But any particle to move in a circular path, this is the topic we had already covered in our basics of physics. Any particle to move in the circular path, we need a force called a centripetal force. What is this called? Centripetal force, which is always directed towards the center, towards the center. So this Fc is equal to the centripetal force minus centripetal. You know, any force which is equal to mass into acceleration. When it is centripetal force and this acceleration is called centripetal acceleration. You know what is the centripetal acceleration? Centripetal acceleration is equal to v squared by r. So this is a very important expression. Centripetal acceleration is equal to v squared by r, where v is velocity of a body moving in a circular path. That may be constant or not constant. Remember once again, this velocity of a particle moving in this circle. Velocity of a particle, how you will find which is moving in a circle? By drawing the tangent here. At this instant, if you want to find the velocity of the particle, so you need to draw a tangent line like this. So that is the velocity. At this instant, if you want to find, so draw the tangent. That is the velocity. Okay. So velocity at any instant in a circular path, you will find it by drawing a tangent line. So that is this velocity. This is maybe constant or may not be a constant. The magnitude. Remember. Acceleration, which is centripetal acceleration formula is how much? V square by R. Remember this. Now, any body to move in a circular path, we need a force called centripetal force, and the centripetal acceleration also will be acting in the same direction because acceleration is in the direction of the force. Okay. Now, one more point here. This is the centripetal force is always provided with some other force. Okay. Remember, for example, there is a planet revolving around the sun. Okay, planet revolving around the sun. So the force between these two is the gravitational force. Will you agree with this? The force between these two is the gravitational force. And that gravitational force will be acting as a centripetal force, my dear students. See here, there is no centripetal force actually, but the gravitational force is acting as a centripetal force. If this is the planet, this is the sun, okay, this is the planet. So there is a gravitational force between these two, okay. So that always directed towards the sun. That gravitational force is the centripetal force in this case. Let's take another case. There is a center here, and the other end of this thread. This is the thread or a rope. So there is a stone. Okay, there is a stone here. This is the center. Oh. So this is the stone is whirling now, which means rotating. So in a horizontal plane, so the stone is rotating here. If you carefully ups. Okay. So when the stone is rotating, so this will become the radius of the circular path. And you know, there is a tension force will be acting towards the center of the circular path, and this tension force is equal to centripetal force minus 2. Here also there is no centripetal force actually, sorry. Centripetal force. Here also there is no centripetal force. But the tension developed in the string is acting as a centripetal force. Alright. This is a simple concept of a circular motion. Clear? Now, one more point here. This is the circle. Okay. This is the midpoint of the circle. Just now we have concluded that this is our centripetal acceleration. This is our velocity direction, right? So when this is the velocity direction, we know acceleration is equal to change in velocity by time. I'm talking about instantaneous acceleration is equal to dv by dt. So this is v. So what is the direction of the v? Right? In the same way, acceleration will be acting. So this is the direction of acceleration. This direction of acceleration, this is called tangential acceleration. What is this? If any body is moving in a circular motion, there will be two accelerations present. One is tangential acceleration, A sub x t. Tangential acceleration. The other one is centripetal acceleration. Okay, so the resultant acceleration will be, this is the resultant acceleration. What is the resultant acceleration? Which is equal to square root AC square plus AT square. You can see the resultant acceleration is always like this. So because the angle between tangential acceleration and centripetal acceleration is 90. Not only here, at this point if you want to find centripetal acceleration will be directed towards the center, tangential acceleration will be like this. So the angle between them is 90. So the resultant will be in this way. Alright, resultant acceleration. Any body is moving in a circular path. remember, any body is moving in a circular path. 100% it will have two accelerations, tangential and centripetal. The resultant acceleration will be like A is equal to square root at square plus AC square. So circular motion, this is the in detail and in-depth analysis. No question will be missed if you learn circular motion in this way. Now, the difference between the circular motion and rotatory motion we are going to. Here the circular motion, the particle is moving in any circle. So the circle may be small, circle may be medium, and circle may be big. Fine. The rotatory motion is the rotatory motion will have a fixed axis. Is that a fixed axis? All right. So what is that? The concept of fixed axis. Let's learn. So the topic of our interest is rotatory motion. Look at here. Imagine this is the midpoint. I'm just drawing the blades of the fan. Okay. This is one blade and this is another blade and this is the another blade. So these are the blades of the fan. So this is the midpoint. So about this axis, so imagine the fan is rotating. So let's concentrate on 2 points. This is A and this is B. Okay. How the particle A is moving. So the particle A is, if the fan is rotating, the point A is rotating like this. So this is a circular path. The path taken by the particle A is what? Straight line path? No. The path taken by the particle A is a circular path. Path taken by the particle P is also the circular path, my dear students. It is also the circular path. But both the particles are making the circular motion about a fixed axis that is called the rotatory motion. About a fixed axis. So imagine at the starting time, when the time is 0, the particle A is here. When the time is after some time, so the particle is at A dash position. So B is the initial position of the particle. After some time, B dash is the final position. How the particle A to A dash move in this way. How the particle is moved from B to B dash. This is called the rotatory motion. It's so simple. Circular motion is taking place about a fixed axis. So that's called the rotatory motion. Okay. Clear? Now, what we are going to discuss here is in rotatory motion, there are some important terms we need to understand. Important terms. That may be the circular motion, right? In the circular motion and rotatory motion, two important things. So not two, so some important terms are there. Number one is radius vector. Number two, angular displacement. Number three, angular velocity. Number four, angular acceleration. Right? So these are the things we need to focus. And the radius vector is denoted with the symbol r. Angular displacement is denoted with the symbol theta. Angular velocity is denoted with the symbol omega. And angular acceleration is denoted with the symbol r. Alright? So let's have a look at one by one. Radius vector. Let us take a circular path. With a single circular path, we can understand all the terminology here. So this is a circular path. Imagine the center point of the circle. Center point is O. Imagine the particle is at this position. A particle is A at this instant. So after some time, the particle will be moved. In a circular path, it is moving. It is moved to the position called A dash. If you understand, if I draw a straight line from the center of the particle, center of the circular path to the instantaneous position, to the instantaneous position, that is called the radius vector. Understand? It is a straight line drawn from the center to the instantaneous position of the particle. That is called the radius vector. And another radius vector I can draw here. So the particle is at D dash now, so the straight line that we draw here. Understand? So that is also the radius vector. As it is a vector, it is having a direction. Direction from initial point to the final point. Initial point to the final point. So that's called the radius. To move from A to D dash, the particle will take some time. Imagine, in time t is equal to 0, this is at this point. After some time t, this is at this point. So, the radius vector is made some angle here. So, that angle is theta. You know, the radius vector is made some angle here, that is theta. So, that theta is called angular displacement. Right? So what is angular displacement? The angle made by the radius vector when it is moving from one point to another point. When it is moving from one point to the another point. So first is radius vector is a straight line between O to A or A dash, anything. Angular displacement is what? Angle made by radius vector from A to A dash. Not only from A to A dash, A to any point. Okay. In angular displacement, there are so many things to be understood. Right? So many things. Angular displacement. Carefully see my students here. So this is the angular displacement can also be called as a plane angle. What is that? Plane angle. So we have the formula for the plane angle. Plane angle is equal to length of the arc by radius. Do you remember this one? Length of the arc. It's A dash here. A dash is the length of the arc by radius of the circle. Okay, so that's a plane angle. Now, that is only angular displacement. Here, one important thing here, this is the angular displacement. We have the SI unit called radian. What is that? SI unit called radian. It is denoted with the symbol RAD. Here, for one complete revolution, look at it. Particle is started from A and moving like this. You can see it is completing one revolution. So can I say that theta will be 2 pi? Yes or no? Can I say that theta is equal to 2 pi? What is the theta? So theta is 360 degrees, right? So theta is equal to 2 pi. 2 pi is equal to 360 degrees. Carefully see. So theta is how much? 2 pi radians, which is equal to 360 degrees. So this I can also write it as 2 pi into 1 radian, which is equal to 360 degrees. From here I can write 1 radian is equal to 360 degrees by 2 pi. Remember this is a very important equation. 1 radian is equal to how much? 360 degrees by 2 pi. Okay. This is for one circular one, right? One complete revolution. So 2 pi is the radius. Okay, because it is 1. When the particle is completing n revolutions, so then the theta, angular displacement will be 2 pi into how many revolutions? N. Remember this formula. theta is equal to 2 pi n. Okay, so this is the interesting part in angular displacement topic, my dear students. Very interesting part in angular displacement. Now, one more important point. You know about the linear displacement, right? So you know about the linear displacement. So the linear displacement, so that is a straight line distance between A and B. Understand? Straight line distance between A and A dash. So that's called linear displacement. So in this case, let us talk about the linear displacement. And another case also. Let's take our fan situation. We come back to a fan situation. This is called angular displacement, isn't it? For A to A dash and B to B dash, angular displacement is same. Understand? So theta is same here. Theta is same for this A to A dash, for this B to B dash. Right? So the blade is rotated in the same angle to move A to A dash and to move B to B dash. The linear displacement you see here. This is the initial linear displacement. And the next step, the linear displacement is here. See here, linear displacement is changing. Okay. So next, if you take the point C to C dash, so the linear displacement will be somewhat bigger than this. Linear displacement, see small line, big line, and so much big line. So the linear displacement is increasing. Understand? Linear displacement is increasing. So, but the angular displacement, that's called the length of the arm. Okay. So L is the linear displacement is increasing, and theta is same here in rotatory motion. From point to point, linear displacement varies and the angular displacement remains same. Okay, clear? So this is about the point called the angular displacement. Now we should focus on angular velocity, my dear students. Simple. Angular velocity. Before moving to the angular velocity, we have the linear velocity. What is the linear velocity is equal to linear displacement by time. Okay, so just straight line. Velocity is equal to displacement by time. So angular velocity is denoted with the symbol omega. Okay, so this angular velocity, let me write the average angular velocity is equal to displacement. Angular displacement, which is delta theta by delta t. Understand? So this average angular velocity. When this delta t tends to be zero, when this time interval is very less, and we write, so instantaneous, we write instantaneous angular velocity, instantaneous angular velocity to dt theta by dt. So this is the angle. Same. What from where I wrote this formula? I wrote from here. So linear velocity is equal to linear displacement by time. Angular velocity is equal to angular displacement by. Okay. Clear? So this is instantaneous angular velocity. Questions will be asked like this, my dear students. Given theta is equal to 4t plus 1. So find the instantaneous angular velocity at t is equal to 1 second. Okay, so instantaneous angular velocity is d by dt of theta. So which is d by dt of theta is 4t plus 1. So this I can write it as 4 into dt by dt plus d by dt of 1 is 0. So your answer is 4. So angular velocity omega is 4, which is having the SI unit radian per second, because you can see here this is radian. Understand? This is radian and this is second. So SI unit is how much for angular velocity? Radian per second, my dear students. Right? Here, one more important point I would like to tell you. See, like these questions also will be asked. So one more important point I just wanted to tell you. Just now I have told you your theta value is 2 pi per one revolution. Per one revolution. So the time taken to complete one revolution is time period. Will you agree with this? From the lower classes, you might be learning the same time taken by the particle to complete one revolution is the time period. So in this case, angular velocity is how much, my dear students? Angular velocity is equal to delta theta by delta t, delta theta by delta t. What is delta theta here? It is 2 pi initially starting from 0, and it is finished one circle. Delta theta is 2 pi and the time period is t. For this, omega can also be written as 2 pi divided by t. 2 pi divided by t. What is this 2 pi? 2 pi is theta, 2 pi radians per second. So this is omega is 2 pi by t. This I can also write it as omega is equal to 2 pi to 1 by time period is the frequency. This can also be written. Okay, so this is angular velocity, and this F is what? Angular frequency, number of oscillations in 1 second. Understood? Clear? This is about angular velocity. Now, let's discuss about angular acceleration, my dear students. Angular acceleration, which is denoted with the symbol alpha. So simple. Generally, acceleration is what? Change in velocity by time. Right here, angular acceleration will be equal to change in angular velocity. Here, linear velocity, change in angular velocity, delta omega by delta t, and this is average. And if you want instantaneous, alpha instantaneous will be equal to d omega by dt. Simple. D omega by dt. Here also omega can be given in terms of time. You can find the differentiation. Okay. So this is SI unit is radian per second square. So this is SI unit of angular acceleration, my dear students. SI unit of what? Angular acceleration. Like these questions will be answered. Now, what we have discussed so far is theta, angular displacement, omega, angular velocity, alpha, angular acceleration. Right? Now, let's see a note how the questions will be asked on this. How the questions will be asked on this. Let us have a look at it. Angular velocity of a second hand in a clock. They are asking you to find angular velocity of a second hand. Omega is equal to 2 pi by t. Second hand. 2 pi by time taken. Time taken by the second hand to complete one oscillation. So if you consider this is the clock, imagine it is a second hand. So time taken by the second hand to complete one circle. Sorry. Time taken by the circular path, time taken by the second hand to complete one circular path is how much? So can I say it is 60 seconds? Second time. One complete rotation means it is finished 60 seconds. So time period is 60 seconds. So this is pi radians by 30 seconds. So the answer is pi by 30 radian per second. Okay. So now the class work is like this, my dear students. Find the angular velocity of a minute's hand. Find the angular velocity of what? A minute's hand, and find the angular velocity of the hour's hand. Okay, so you find the angular velocity of these two. Just this is the class work. Right? Now, here itself, we are going to learn an interesting point here. Very interesting point here. Relation between V and omega. What is V and omega? V is linear velocity. Omega is angular velocity, my dear students. V is what? Linear velocity. Omega is angular velocity. Now, we have L is equal to R into theta. From where? From here. This is R point A. After some time, this is A dash theta. So this is length of the arc. Both the sides, this is from plane angle only. Plane angle formula is what? So theta is equal to L by R. That's a plane angle. Okay. So L is equal to R theta. Both sides, if you differentiate with the time, both sides, if you differentiate with time, d by dt of L, it's a velocity. D by dt of linear displacement is velocity. So this R is a constant. D by dt of theta. What is d by dt of theta? So d by dt of theta, again, d by dt of theta is omega. Understand? Clear? That's an instantaneous velocity, instantaneous angular velocity. Okay? L is equal to r theta. Differentiation both sides, we get V is equal to r omega. Okay, for your better understanding, and let us remove this. Now, write it once again. So dl by dt, which is equal to r into dt by d theta by dt. What is d theta by dt? Here somewhere we discussed, right? Instantaneous omega is d theta by dt. So the same thing. So let us write here v is equal to r into omega. Okay, v is equal to r omega. Linear velocity is equal to r into angular velocity. Okay, when r is constant, when r is constant, v is directly proportional to omega. When r is constant. Now, when R is equal to constant. And one more interesting thing you see. We are talking about all these things when a particle is moving in a when a particle is moving in a circular path. You know, centripetal acceleration is equal to V square by R. So here V is equal to R omega, right? I can write R square omega square by R. Just substituted V is equal to R omega. What R gets cancelled. So this will be R into omega square. So centripetal acceleration can also be written as R into omega square minus x. Okay, clear? Now, what we are going to discuss is in this rotatory motion or circular motion R and circular motion, how the equations of motion will change. So that's what we need to discuss. Let's have a look at this. We have V is equal to U plus AT, right? V is equal to U plus AT. S is equal to UP plus half AT square. V square minus U square is equal to 2AS. So this is in the linear motion we have minus units. Whereas in the circular motion, the same equation will become like this. Let's have the same equation will become like this. This is V linear velocity, this is angular velocity. So final angular velocity is equal to initial angular velocity plus angular acceleration into t. This one. So linear displacement, and that will become angular displacement. Angular displacement is equal to initial angular velocity into t plus half into angular acceleration into t square. So from here, v square, which is omega f square minus omega I square, which is equal to 2 into alpha into theta, because A is linear acceleration, alpha is angular acceleration. S is linear displacement, theta is angular displacement. So in this way, equations of motion will modify in circular motion or in rotational motion. But equations of motion are valid when a particle is moving with uniform acceleration. This you know, uniform acceleration. Here also, the particle is moving with a uniform angular acceleration. So then only these equations of motion are valid. Otherwise, no. Okay, clear? Now, our topic of interest is a uniform circular motion. What is this? Uniform circular motion. For a short form, I can write UCM, uniform circular motion. Simple. Wherever there is a term called uniform, right? You know, uniform motion you know. Okay. Uniform motion you already know. In uniform motion, can I say the speed is constant? Yes. Uniform motion speed is constant. Uniform circular motion also speed is constant. Remember, speed is constant. Speed is what? A scalar quantity. Remember? It's an easy way of remembering, recollecting the concept called uniform circular motion. Speed is constant. As speed is a scalar quantity, all the scalar quantities, energy is also constant in uniform circular motion. Right? Velocity, momentum, momentum, acceleration changes in uniform circular motion because they are vectors. Because they are vectors. Clear? Now, this is not the detailed concept. Now the details will start. Details. Okay. This is the middle point here. Imagine the particle is starting from here, moving here, here, and here. At this instant, the particle is moving with a velocity. At this instant also it is moving with some velocity. At this instant also it is moving with some velocity. At this instant also it is. So because velocity of the particle in a circular motion, I've told you already, we will measure by drawing the tangential line, tangential line, tangential line, tangential line. It's a velocity, a velocity, a velocity, and velocity. Very important thing is, in uniform circular motion, the uniform circular motion means when a particle is moving in a circular path with a constant speed, with a constant speed, that is called uniform circular motion. If a particle is moving in a circular motion with a constant speed, that's called uniform circular motion. Okay, so this is velocity constant. Sorry, velocity, speed is constant. That's why I wrote magnitude of this velocity. Magnitude of that velocity is constant. Magnitude of the velocity is constant. Magnitude of the velocity is constant. Magnitude of the velocity is speed. Okay, is constant. Alright. Alright, but the velocity is changing. Velocity is a vector quantity which will have direction. Direction is changing, you can see. Here, the direction of velocity is upwards, here left side, here downwards, here right side. See? At any instant you take, the direction of velocities keep on changing. That means the vector quantity is changing, even if its direction changes. But the speed is not like that. Speed will not have any direction. It has only magnitude. That magnitude is constant. If a particle is moving in uniform circular motion, what happens? If a particle is moving in uniform circular motion, carefully see, it will have a centripetal acceleration which is equal to v squared by r. It will have a tangential acceleration. I told you already. The tangential acceleration is equal to rate of change of velocity. Carefully see here. So this is constant. Yes or no? V is constant in this case. V is constant. So when d by dt of constant, it is zero. So that means in uniform circular motion, tangential acceleration is zero. So there will be only centripetal acceleration. In uniform circular motion, only acceleration. Net acceleration is centripetal acceleration. Okay, clear? This is the uniform circular motion, right? So here, one more thing you need to understand. So this I can also write r omega square. Remember, in terms of omega. This omega is equal to what? 2 pi by time period, which can also be written as 2 pi into frequency. Okay, so this in terms of frequency also, if you write this acceleration in terms of frequency also, if you write it, centripetal acceleration is r into omega 2 pi f whole square. Okay, this is also correct. Now, non-uniform circular motion. What is this? Non-uniform circular motion. Non-uniform. Let's take the same circular path here. Same circular path. See here. There is a set. See here also circular motion. Whatever it may be, it is a circular motion. Centripetal acceleration is compulsory. This is what the tangential acceleration is also compulsory. Unfortunately, the tangential acceleration has become zero in uniform circular motion because speed is constant. In non-uniform circular motion, speed also varies. Speed also is not constant. Here the speed may be 20 meters per second. Here the speed may be 30 meters per second. But the direction will be tangential. So here the speed may be some 40. So let me say here the speed is V1, it's a V2, it's a V3, and it is a V4. At each and every instant, the speeds are different. So that's what speed is varying. In non-uniform circular motion, speeds are different. As the speeds are different, so speed is increasing, right? So that is why this is the tangential acceleration direction and the speed direction. When the speed is increasing, tangential acceleration and the speed and the velocity directions are same. Okay. So in this case, if you carefully observe the resultant acceleration will be like this. If the starting of the chapter itself I have told A is equal to square root tangential acceleration square plus centripetal acceleration square. Here one important and interesting thing to tell you, dt is equal to dv by, sorry, at is equal to tangential acceleration is dv by dt. So this is important. d by dt of v is equal to r omega. Can I write like that? V is equal to r omega. V is equal to r omega. Yes, this is the relation between linear velocity and angular velocity. So the tangential acceleration is equal to, carefully see, R into d omega, R is constant, okay? D omega by dt is angular acceleration, okay? So remember this, my dear students. Tangential acceleration is R alpha and centripetal acceleration is V square by R, which is R omega square. So these two I can substitute here. So net acceleration in this case, tangential acceleration is R alpha whole square plus centripetal acceleration is R omega square whole square. Understand? Remember this equation. Okay, clear. This is about a non-uniform circular motion. And here, one interesting thing you need to understand the difference here. Simple, interesting thing. So imagine if it is a particle is moving in a non-uniform circular motion, non-uniform. If a particle is moving with a non-uniform circular motion, see here, if this is the velocity which is increasing, right? So the tangential acceleration also in the same direction. So this is the centripetal acceleration direction. So the resultant acceleration will be like this. Resultant acceleration will be like this. For example, second case, if you consider, this is the centripetal acceleration only. Here, if the velocity is decreasing, my dear students, if the velocity is